I will be talking about prompting today, and this is a rather new topic in NLP, one that's kind of exciting. I'm excited about it because it represents kind of a new way of doing things, a paradigm shift in one way. And so I will be spending one class talking about this, but we also have a bonus part on encoder-decoder pre-training. And the reason why I'm introducing these two different things this time is because you can use encoder-decoder pre-trained models for prompting. So they're both pretty closely related. So I'll talk about these two things together. I'd like to say most of the slides here were created by Pengfei Liu, postdoc in my lab. So thank you, Pengfei, if you're listening. So normally I have a recommended reading on the website for each class. This time I'm going to particularly recommend it. And the reason why is because most of the stuff I say today is going to be in this survey as well, except in more detail. So we just wrote a survey on prompting methods for natural language processing. It came out like 2 months ago. So it's very current, and most of the stuff in the lecture is based on what we did here. So there's also a website with a nice cartoon on it with lots of characters that pre-trained language models are named after. Okay, so the first thing I would like to do is I'd like to do a little bit of a recap of some of the stuff that we have talked about already to put in context the idea of what prompting is compared to previous ways we did NLP. And there are kind of 4 paradigms of NLP technical development that we've experienced over the past decade or so. The first one being feature engineering. The second one being architecture engineering, objective engineering, and prompt engineering. And so what do I mean by this? So feature engineering is something that used to be one of the main things that you would do when you were developing an NLP system. It still kind of is implicitly instead of explicitly, but it used to be that you did explicit feature engineering to try to make your systems better. And what I mean by this is basically you would have a fully supervised learning model. Usually these were not neural network models. And up until about 2015, this was popular. And what you would do is you would have a non-neural machine learning model, and you would manually define feature extraction functions. So this is what I talked about at the very beginning of the class, right? We would identify, we would want words to be extracted from a text, and then we would feed these words into a linear classifier. And these would, if the words were not sufficient, then we would extract bigrams, or we would extract the fact that there was a negation in the sentence and it was negating a particular word, or other things like this. And after we extracted all of these manual features, we would feed them into something like a support vector machine or a naive Bayes model or something like this. Or conditional random fields if you were doing something like sequence labeling. I'm probably going to talk about these maybe next time. Then after that, the next paradigm is architecture engineering. And basically, we would use fully supervised learning with neural networks. And this was quite popular from kind of maybe 2013 or so to 2018. And this would rely on neural networks to be our feature extractors instead. So now instead of manually defining feature templates, we would extract them using RNNs or whatever else. However, because we would no longer be defining features, we would choose our network architecture very carefully. So we would choose like an LSTM because it was good at passing information over long distances. Or if we wanted to do text classification, we might use something like a convolutional neural network, which kind of allows you to extract local features more effectively. Most of the time, we did not use the kind of pre-training techniques that we talked about before Or if we use them in something like Word2Vec, which I'm sure a lot of people have heard of. But basically, they would extract only the embeddings in the first layer of the model as opposed to pre-training the whole model. One example of this might be using convolutional neural networks for text classification. Then we can think of objective engineering. And basically, this is the pre-train and fine-tune paradigm, like I talked about last lecture. It became very popular with Elmo, even more popular with BERT. So it's kind of 2017 and still, very popular nowadays, of course. And pre-trained language models are used as the initialization of basically the full model, using both shallow and deep features. But on top of the feature extractors that you get from these pre-trained language models, you also apply a classification function that predicts your topics for you or predicts your sentiment for you or something else. So you do have a few extra features that you add on top to make this classification decision. An example being BERT and then fine-tuning for your task. So then what we're going to talk about today is something that we've been calling prompt engineering. And basically what this means is you pre-train a model, you design a prompt that specifies the thing that you would like the model to do, and then you make a prediction. So we've kind of tried to come up with a semi-catchy name for this: pre-train, prompt, and predict, or P3. And basically, this has become popular in mostly in 2019 up until now, and still a lot of interest in this as well. So the characteristics of this are that NLP tasks can be modeled entirely by relying on language models. And in the extreme, we don't even do additional training of the language model. We can just use the language model itself to solve NLP tasks. And I'll give some examples of this in a second. And shallow and deep feature extraction, as well as the prediction of the output, are all done by the language model. However, in order to, because prompts are used to specify the task that you would like the language model to perform, you need to be very careful in your design of the prompts in order to allow them to cause do a particular thing. And one example of this that made this very popular is GPT-3, a large language model that was combined together with prompting. So what is a prompt, or what is prompting? It's basically encouraging a pre-trained model to make a particular prediction by providing a prompt specifying the task to be done. And most typically, this is done by basically giving a textual prompt, or in the simplest form, this is done by giving a textual prompt like this. So if you have a language model, you ask the language model, JDK is developed by, and then you ask your language model to fill in the blank, and it will give you the answer oracle, for example here. Or if you put in a super long text here, and then you have a big language model that was trained on the internet, and you write TLDR. Maybe the language model has seen so many TLDRs that it already knows that it should be summarizing in this particular case. Or birds can blank, and you can have fly. So this would be kind of like factual knowledge or common sense knowledge. And if you want to play around with this, you can. I can give a few examples. We can go to the. We can search for like Ellen NLP demo. And go to the demo here. And then we go to masked language modeling. And we put in an example. So let's see. Carnegie Mellon is located in Mask. Oh, wait, sorry. Should add a period. Pittsburgh. not bad. What else should we do? Let's do, well, most birds can fly. Some cannot, such as. Okay, so it's not perfect. This is also BERT. So BERT is an older, smaller model than some of the newer models. So you might be able to do better with other ones. Another one that people may or may not be familiar with, there's a really nice large open source language model that you can use recently called GPT-J. And I'll give an example here. Maybe we could do, let me try to find a random text that we can put in here. And this is something, you know, I encourage you to do yourself if you're interested. So I'll copy in the first article from the New York Times and put TLDR and see what happens. This will take a little bit. Oh, or maybe I won't. So, oh yeah, there we go. Huh, that is strange. It's removed my TLDR. So that may take a little while. So a few highlights from the interview are that he is open to cuts in Medicaid funding. He would like to see this. So it's generated, you know, individual bullet points to kind of summarize the content up here. Pretty good, huh? So this is kind of the power of like a general purpose language model that never has been explicitly trained to do like TLDR style summarization, but it's seen lots and lots of data like this on the web. And so the idea behind prompting is that it allows you to do kind of this sort of multitask prediction, even for tasks that haven't been explicitly specified in your data. So hopefully that was a kind of interesting demo that shows you why people might be excited about this idea. And now I'm going to go into the details. And this has been a really popular research area over the past couple of years. So there's a lot of kind of cutting edge research on this topic. So what is the general workflow of prompting? It basically is split up into prompt addition, answer prediction, answer label mapping. And I'll go through each of these in turn. So prompt addition, basically what it is it, given an input X, we transform it into a prompt X prime through 2 steps. First, we define a template with 2 slots, one for the input X and one for the answer Z. We fill in the input slot X, and given this, we generate a prompt that we will then ask the model to fill in. So for example, let's say our input X is I love this movie. And then our task is sentiment analysis. So we've designed this prompt where we first prepend the sentence that we would like to do sentiment analysis of. And then in the end, we have overall, it was a Z movie. And so that gives us this prompt X prime. Another example of this might be, let's say we wanted to do relation extraction over locations. or we wanted to predict location relations, we would have like Pittsburgh. Pittsburgh would be our input X, and our prompt would be X is located in Z. And another example would be like X TLDR if we wanted to do summarization. So the next part, the next thing that we do is answer prediction. So given a prompt, we predict the answer Z. And we do this with the language model. And I love this movie. Overall, it was a fantastic movie. So that's kind of what I demonstrated through the demo before. And then in the end, this is kind of an optional step. You won't do it every single time, but you would do it for things like text classification. And basically, given an answer, you would map it onto a class label. So if we have the word fantastic here, we might have a mapping from fantastic to positive. So this is the whole process that you could use to generate an answer according to this, procedure. Are there any questions about this? Pretty straightforward. Okay, great. So the next thing I'd like to talk about is a couple types of prompts that we have. And the first one is a prompt. What we're calling basically a prompt is a prompt where we've had X filled in. We also in the survey paper call it a prompt template if X is not filled in. This is the prompt that we provide to the language model. We also have filled prompts, which are prompts where we predicted Z, and answered prompts where we predict Z with, we basically have provided Z with a correct answer here. And the reason why we define this separately is because these can be used to kind of teach the model in a more effective way what it should be doing by providing it some examples of correct answered prompts. And we also distinguish between two types of prompts: prefix prompts, where all of the input, or Z is the last item in the sequence. And the reason why these are useful is we can contrast them with closed prompts, where Z is not the last item in the sequence. And some of these are more conducive to using certain types of language models. So like the language models you might want to use a autoregressive language model to solve this one, or a mass language model to solve this one. So I'll describe in a little bit more detail later. So I had a question: why does prompting work better than objective engineering? That's a good question. These are not actually mutually exclusive. One major advantage of prompting is that you don't need to know what task you want to handle before training. And by just adjusting the prompt, you can have a language model solve a pretty wide variety of tasks. So basically, prompting is more versatile. Objective engineering could still be useful if you design an objective that allows you to more effectively answer particular questions. So just to give one example, if you want to, you might, in addition to having a language modeling objective, have an objective where you solve lots of question answering tasks. And then that might make your model more versatile, more able to solve QA style questions, and that would make it easier to prompt the model as well. So you could use both of them together. Anything else? Okay. So some design considerations that you would want to think of if you're using a prompting method is, first, which pre-trained model should you be using for this? Second, prompt engineering. So how will you design your prompt to use? Also answer engineering. and ways you can expand the paradigm between the simplest example that I just talked about before, and also prompt-based training strategies. So where you actually train your model together with some prompts. So basically we have in the survey paper that I introduced earlier, we have this big typology of things that you need to worry about. And I'm going to be going through each of these one by one. So first, talking about pre-trained model choice, we have lots of choices for models. The first two I basically talked about already. These are left to right language modeling and mass language modeling. And then the second two are kind of new things that I'm going to be talking about this class. So left to right language models, because we've covered them already, I won't go into a bunch of detail, but interesting tidbit, we've all heard of Markov models. Markov models were first, does anyone know what Markov models were first designed to do? Any ideas? What were they first applied to? Yeah.
Was it weather prediction?
Weather prediction, no. Speech, no.
The other good choice would be atomic bombs.
Atomic bombs, no, not atomic bombs, not post-tagging in NLP, not stock markets, not OCR, no. Lots of good good potential choices that are all wrong. There's a hint that it's 1913, so it probably wasn't atomic bombs, but like the Markov first used these to predict the character distribution in a Russian novel. So they literally were a language model from the point when they were very first invented, and it was actually a character level language model. So, you know, he knew what he was doing. So count-based, originally they were count-based, so basically count and divide style models. Now we use neural network-based models. So, you know, some examples of this could be GPT-1, 2, 3, etc. When you use them in prompting methods, these were kind of the earliest architectures chosen for promptings, and they're usually used with a prefix prompt. And often the parameters of the pre-trained language models are fixed and just used as is. So that would be like the example of the TLDR with GPT-J that I was talking about before. Second one is mass language models. So, you know, these are bidirectional prediction. These are often used more for like NLU tasks, natural language understanding, instead of natural language generation tasks. And examples could be Bert or Ernie or any of the other Muppets. And their roles in prompting methods are usually they're combined with closed style prompts. So that was like the example of Carnegie Mellon is located in mask period. So you can use them for things like that. And you formulate any of the NLU tasks that you'd like to solve as a closed task. So a prefix language model is like kind of a combination of a left to right language model and a masked language model. And basically what you can do is you use a single transformer, but you use two different masking mechanisms to encode the X side, the input, and the output. And basically for the input, you can use bidirectional masking to encode information in both directions. And for the output, you use autoregressive left to right masking to make sure that you can predict the output from left to right. So these are pretty commonly used as well. And when you're pre-training the models, you can also introduce corruption operations when encoding X, like you have for Bert, for example. And there's a couple examples of this, like UNIT-LM and Ernie-M, for example. For encoder-decoder models, the characteristics of these are they use denoising autoencoders, and you usually use two differently parameterized transformers, one kind of encoder style transformer and one decoder style transformer over here. You know, we already talked about this in the attention class. So this is like the same thing that you would use for something like machine translation, but you can also do pre-training with these models as well. And some examples include BART and T5. So I'm going to go into a little bit more detail of these encoder-decoder pre-training or prefix language model pre-training methods. And there's some representative methods called like MAS and BART, unit LM, T5. These are all, MAS is kind of the predecessor to BART and T5. BART and T5 are actually used quite widely nowadays. So I think they're good models to know of and use in your own work if you're interested. So MAS is one of the earlier kind of instances of this encoder-decoder pre-training. And basically what they did was they took an original sentence and they masked out some part of the sentence. And then they had a model on the output side that basically input masks here and then predicted only the masked out part of the sentence. So this is kind of like a denoising autoencoder or like a masked language model like BERT, but applied to the encoder-decoder framework. And it was trained on lots of web text. So BART, on the other hand, is a slightly newer version of encoder-decoder pre-training. One important characteristic of BART is that BART always reconstructs the original text. And so because of this, the decoder is always reconstructing good English, or, you know, in the case of MBART, which I'm going to be talking about next time, it's reconstructing good language in whatever language it's trained on. So because of this, this is particularly good for tasks where you want to generate language, because during its pre-training, it's always, you know, the decoder is always being trained on good text. And what they do is they do a bunch of different corruption operations on the input. So they do things like deleting some tokens from the input, also masking out some tokens from the input, permuting the order of sentences, rotating a document, and also text infilling here is like adding extra like things inside the text that you will then fill in. And in all cases, they're trying to reproduce the original text. So MBART is a multilingual version of BART, and it's essentially, you know, exactly the same objective, but it's trained on 25 languages. So because of this, you can use it in multiple languages if you want. Only 25, but that's still a decent number. Another example is unit LM. So this is the best example I know of a prefix language model. And basically, it's trained in the way that I talked about before, with a bidirectional mask on the input, a unidirectional mask on the output. It's also trained using just unidirectional masks, just bidirectional masks, etc. So that allows you to encode in either both directions or in a single direction, depending on what task you want to solve. And then finally, T5. T5 is essentially an encoder-decoder model. And one thing about the T5 paper is it actually presents a pretty extensive exploration of different aspects of pre-training these sorts of models. So the paper actually is quite good. I'd recommend. Often pre-training papers, you know, are like minimally useful in terms of new insights, but they are very good in terms of new resources that you could use in your research. But this one actually has a fair number of insights in it as well. So I would recommend you read it. But one of the interesting things that they do is examine different types of training objectives they use, and they also examine different sizes of data they use to check the effect of the size of the data. And basically, they here are some of the objectives they use. Sorry, this is pretty small, but you can also look at the survey paper. But they test prefix language modeling, where they basically have an encoder, and then they decode the rest of the sentence. They have a BERT-style masking objective, where they try to reproduce the original text. Deshuffling, mass-style objective, like I talked about before. Replacing spans, dropping tokens, and randomizing, like randomly selecting spans to drop out and then replacing them. So, and they have some examinations of which objectives are better for training the model as well. Okay, any questions about these? Oh, one thing I forgot to mention is that there's also a multilingual version of T5. So T5 was created by Google, BART was created by Facebook. So whatever one does, the other has to do, because they can't share anything for some reason. But one good thing about MT5 is that it supports many more languages than MBART does. So it supports 100 languages, which is not 7,000, but it's more than 25. So it's it might be useful in that capacity. Cool. Yes.
Can we not include the prompting feature in the training as well? Like, actually, you would ask a description about your previous task, and then train a model on top of it, so that I understand that there's a description that comes to me at my giving, and this is what I'm supposed to understand the task, and that's what I'm.
Yeah, that is possible. We'll talk about that a little bit more later. Cool. Any other questions? Okay, great. So if you want to use either of these methods in prompting, these are particularly useful for things like conditional text generation, like translation or text summarization, generation like tasks. So things like information extraction, question answering. It's a little bit less straightforward to think about exactly how you should be using these models in a prompting style approach, because you need to think about what corruptions were applied to the original input and how can I apply something that looks like those corruptions so that it reproduces the original output. So kind of intuitively, we can understand fill in the blanks like what we had for BERT, or how to continue a sequence like we had for the left to right language models, but these ones are a little bit like maybe a little bit less straightforward to wrap your head around. Okay, so that's the first part. Now I'm going to talk a little bit about prompt engineering. There's actually quite a few methods to allow you to do things like this, but I'm only going to cover some of them, and then if you're interested, you can take a look at the survey as well. So compared to the original traditional formulation where you would do something like this, you need to do where you do input and you would predict the output. Here you need to do input, you need to create a template, turn that into a prompt, make a prediction, and do a mapping. So the first question you need to answer is, how do we define a suitable prompt template to solve any particular task? And especially in the case where we're just using a regular language model, obviously this is extremely important because it can do many tasks. So the only thing that will decide which task it does is the template that you're using. So if we split this up a little bit more, how do we define the shape of a prompt template, and how do we search for appropriate prompt templates in the first place? The shape thing is relatively straightforward. So close prompt, we prompt with a slot to fill in the middle of the text, like this. And a prefix prompt is where the input text comes entirely afterwards, like this. And as I mentioned before, this affects the type of model that you can be using. The next thing is how do we actually design the prompt templates? So before you saw me just filling them in manually. And that's certainly one way you can do this. Like one of the nice things about filling them in manually is we, as humans who speak language, specifically the language model is in, have an idea of what sorts of things we might fill in to achieve a particular task. So if we have no data whatsoever for the task, no training data whatsoever for the task, this is the only way we can do it, right? We need to come up with manual templates based on our intuition. On the other hand, we can also do automated search for templates. And there's kind of two types of prompt templates that we could be using. The first one is discrete text in the language that we are, that the language model is working in. And another one, which actually is somewhat popular nowadays, is to do search in continuous space. So not worry about the prompts being in the language that we're interested in, but rather just search for them as parameters of the model. So I'm going to introduce 4 methods. The first one is prompt mining, then prompt paraphrasing, gradient-based search. The first 3 are discrete prompt search methods, and then there's also prompt and prefix tuning, which are continuous methods. So prompt mining, basically what this does is it mines prompts given a set of basically inputs and outputs. And it's particularly useful for things like relation extraction, where we could extract or where we have relatively simple questions and answers that would appear quite frequently in a corpus of textual data. So for example, let's say we want to extract prompts for the was born in relation or birthplace relation. And we have a set of entities along with their birthplaces. If we have something like this, we could then crawl a huge corpus for all sentences that contained one of these 2 pairs, like Barack Obama, Hawaii, or whatever famous person and where they were born. And then you can abstract these away, remove these, grab only the center words, and use this as the prompt that you want to fill in. And then you take maybe the most frequent one or something like that and use this to make your predictions. This is a really old method of doing relation extraction. So this has been around for a long time. And there were many methods to do this, but this is how you could apply it to prompting. To make this a little bit more sophisticated, one thing that you can do is you can look at the dependency path between the words. And this is useful if you want to extract anything other than the middle words here. So basically what you do is you do dependency parsing, which we're going to be talking about in a few classes, to get kind of the syntactic structure of the sentence. And then you grab the whole path of dependencies between the 2 words and use that to extract your prompt here. So that's another method you can use. Another thing that you can do is prompt paraphrasing. So like, let's say you have a halfway decent prompt that a human has created just based on their intuition, or a prompt that you mined. One thing that you can do is you can paraphrase them. And you could use basically any paraphrasing model that you want, a state-of-the-art model to paraphrase 2 sentences. Specifically in this paper, this is a paper by Zhengbao Zheng, one of the students in my lab. But basically what we did here is we translated the prompt into German, and then we translated it back into English. And if you do that, because German and English are different languages, you can get multiple outputs, like has a common border with, adjoins, other things like this. And then you can, if you have a development set or something like this, you can test which one gives you the best accuracy and use that one, for example. Any questions about these? Yeah. Oh yeah, so in terms of paraphrasing, does the syntax of the paraphrase or the variety of the paraphrase depend on the language you're translating to? And yes, it does. If you have a really bad translation model, then that might give you really bad paraphrases, but it also might give you a lot of variety. So, who knows? So yeah, for sure.
That raises the question whether people compare using different languages.
Yeah, we did not compare using different languages here. I'd also like to point out that this is not the only way to do paraphrasing. There are other ways to do paraphrasing, like taking BART or T5 or whatever your favorite sequence pre-trained model is, and training it to do paraphrasing directly. So I think the specific method that we use to do this paraphrasing is less important than just the idea that if you do paraphrasing, you can get more diverse prompts. Yeah. Yeah, so how do you evaluate the quality of the generated paraphrases? So basically, if you generate a whole bunch of them, you want to know which one you use in the end, right? And the best way to do that is if you have a development set where you can evaluate the accuracy of the prompted model according to your development set accuracy. So you would hold out like some examples from the shares a border with relation, and you would see how accurately you can predict those examples using all of the prompts. And if the first prompt gets 70%, the second gets 60, the third gets 80, you would pick the third prompt as the one that you choose. So that's a good question. Wouldn't that miss some good paraphrases that aren't in the dev set? But the way we apply this to the dev set is the dev set is basically pairs of inputs and outputs. So it would be like United States, Canada, France, Germany, and things like this. So it would just be entity pairs. And so what you do is you take United States has a common border with, and it would predict one or multiple outputs, and then you would check whether that matches with the actual knowledge in the output. That's just an example from relation extraction. You could use it for other things as well, but relation extraction is, yeah, but you could use it for other things as well too. Does that make sense? Or, anything else? Okay. So moving on to the next one. So these were kind of like maybe the first two methods proposed for prompt engineering or automatic prompt search. There's been a lot of follow-up work on this, so these are just two additional examples. But this method, which is called Autoprompt, basically instead of like searching for prompts that actually exist in the text, they blank out these prompts, and then they do back propagation into the embeddings here to basically find the ideal embeddings that would give the highest probability of getting the answer correct. And then they find the word that is closest to that embedding, like atmosphere or a lot or dialogue or something. So basically what Autoprompt does is you put in a real joy, and then you will append these like 5 words that happen to be the best words in your vocabulary that would allow you to get the highest probability of getting it correct. And in fact, what happens when you run Autoprompt is it does exactly this. It comes up with completely incomprehensible strings of words that nonetheless way outperform any comprehensible string of words that you're able to come up with in English. So this was somewhat surprising to me. One thing that I don't know about this method is whether this would like transfer across data sets, like be robust across data sets or be robust across tasks or something like this. But nonetheless, it's interesting that basically total nonsense is a better prompt than, you know, the actual like English prompt that humans mining or paraphrasing can come up with. Yeah. Yeah, so would anybody ever use a method like this to do prompting of a model? And that's actually a very good point. Sorry, the reason why you might not want to do that is because the whole point of prompting is to allow you to specify tasks in natural language and do new things. And yes, I kind of agree with that. Let me go to the next slide and then I'll get back to that question. Yeah. Yeah, so this is fixed for the entire task. So you train it once to do well on the task, and then you use it for the task. Yeah, exactly. Yeah. So let me go to the next one and get back to the question that we had before. So the next thing is called prefix or prompt tuning. And so this is search for prompts in continuous space. And the interesting thing about this is now they've completely given up on natural language prompts. And the idea is you append a few tokens to the beginning of the sequence, but instead of appending actual natural language tokens, you just append something like a special token, like token 1, token 2, token 3, like this, however many you want, up to like 200, whatever. And then you directly optimize the embeddings of these tokens. And so that's actually very similar to what we did here with this autoprompt method, except now instead of even trying to turn these back into natural language tokens, we just use these like pseudo tokens as is, and they become our prompt. So we keep the rest of the parameters of, at least in these works, we keep the rest of the parameters of the language model fixed, and just optimize these tokens. So why is this a good idea? Basically, we know that prompting works, and we kind of have an intuitive idea why prompting would work, because the language model has been trained on lots of different data that includes things like TLDR, which are very good indications of what we should be doing next. But by doing this sort of gradient-based search is easier than search in discrete space because you can use backpropagation and all the tools that we already know. And so this will, make it both easier and more effective to find precisely the prompt that would be useful in answering the question or in solving the task. Another thing is there's kind of two very similar or nearly concurrent works on this. One is called prefix tuning, one is called prompt tuning. From the names, you wouldn't have any idea what the difference between them is because, a prompt can be a prefix and a prefix can be a prompt. But basically prompt tuning is optimizing only the input embeddings. So you basically, it's exactly what I said here. You have these pseudo tokens and you're optimizing the embeddings of them. Prefix tuning is optimizing one prefix for every layer of the transformer. So it basically has more parameters. It has as many more parameters as like every layer that you have in the transformer. So it's more heavily parameterized. So going back to the question, why would we even want to generate incomprehensible tokens? Another way you can view this is like the model set I talked about last time, or the methods that I talked about last time for partial parameter tuning. So we're tuning only a very small number of parameters of the model for effective adaptation to new domains. So basically, that's exactly what this is doing here. This is just yet another parameter efficient tuning method like adapters or like the other things that I talked about last time. So the kind of funny thing is that prompting in natural language still is very useful, right? Because a human can actually do this without any training data. It can be used for zero-shot learning where we have no training data whatsoever. But it kind of came full circle back to the parameter efficient tuning methods that we were already using. And now it's inspired new ways of doing this. So I think that's kind of how it brings everything together. I had a question. Would the incomprehensible nature of the prompts in Autoprompt be something you could address with more regularization? Yeah, that's a great point. So like if you had a regularization that tried to maximize the language model probability of the prompts that you derived, yes, you could definitely do that. I don't know of anything that does that, but that's an interesting idea. Yeah. An interesting question is whether that makes it better or worse. So
it might be doing really well precisely because it's hitting a point in the space you can't get to.
Right, it might be doing well precisely because it's hitting a point in the space that you can't get to with natural language prompts. Yes, I totally agree with that. However, there's a very high probability that it might generalize better across language models, or it might generalize better to new tasks if you were in a more like natural place in the natural language space. So I could see it going, like probably on the data set you trained it on, no regularization might be better, but on like other data sets or other language models or something, I think it would certainly be better. Cool. Yeah, any other questions? Okay. So then the next thing I'd like to talk about is answer engineering. And answer engineering is not engineering the input, but rather engineering the set of possible outputs. And so we've reformulated the task of solving any NLP task into something that we can solve through prompting, but we can also redefine the ground truth labels. So here, you know, we had fantastic, and then we had some mapping function into the actual label that we want to predict, which is positive. And so here we have our label space that we would actually like to predict. And then we also have a space of answers that we would accept as a result, that we would accept as indicating that point in the label space. So we have this mapping. This mapping basically needs to be one label to one or more answers in the answer space. We can't have an answer in the answer space that maps to multiple labels and still maintain a deterministic mapping into the label space. So answer engineering aims to search for an answer space and a map to the original output that results in an effective predictive model. So we need to define the shape of an answer, and we also need to decide how to search for appropriate answers. And the answer shape can be one of basically three things. The first is a token. So one token or a set of tokens in the pre-trained language model's vocabulary. It could also be a chunk. So it could be a short chunk of words made up with more than one token. And this is usually used with closed prompts. And it could also be a sentence of arbitrary length, usually used with prefix prompts, where you can just generate the outputs. And which one you choose very often will depend on the tasks. So like if we're talking about text classification, we could choose a token or we could choose a span of tokens. If we're talking about something like text generation, like summarization or translation, we might want a free-form text. If we're talking about something like relation prediction, in the original formulation of relation prediction in a very famous data set called Llama, they basically only allowed single token entities. But then if you're talking about the is a citizen of relation, then you can't predict the United States, right? So that's a little bit of a problem. So there you might want to predict, spans of tokens instead. So once we've defined the space of answers that we can accept, we will choose a search space so we can have it be handcrafted. The simplest handcrafted search space is just to allow anything to be an answer. This is appropriate when free-form text is an appropriate answer for the question for something like summarization or machine translation or something like this. We could also have a finite answer space. So this would be good for something like classification or anything where we're doing like multi-class or binary classification. And we can also do automated search, and this search can be done in discrete space or continuous space. So handcrafting basically, is an art. You figure out what to do based on your intuition. But if we talk about automated search, we have answer paraphrasing, where basically we start with the initial answer space and then use paraphrasing to expand this answer space to be larger. So that's pretty straightforward, right? It's the same as what we had before. And another thing that we can do is we create an initial pruned answer space of several plausible answers. So this can be done through paraphrasing or whatever else. And an algorithm further searches over this pruned space to select a final set of answers. So you could do things like add one as long as it's improving accuracy, reduce one as long as it's decreasing accuracy, etc. Another thing that you can do is decompose each label or decompose like a multi-word label into its constituent words and use each of them as an answer. So like if we have city of death or something like that, it could be like city death. Actually, I'm not sure why person's there. That might be a typo. And then a continuous search space, pretty simple. It's like prefix tuning or prompt tuning like I talked about before. You just use gradient-based ideas. You have a virtual token, and then you optimize the parameters of the virtual token in order to maximize your accuracy. Any questions about this? Yes. Okay, yeah. So basically, we're predicting a token Z here in order to decide what the answer is. And if we didn't do any search, or if we had a manually defined feature space, answer space, if we're doing sentiment classification, you might have like good and bad be your answers that correspond to a positive sentiment and negative sentiment. What you can do instead is you can just make this like a pseudo token for positive, a pseudo token for negative, and then directly optimize the parameters of the pseudo token using backpropagation in order to maximize your accuracy. And this requires that you have some training data. Yeah. There would only be one for each label. You could consider having multiple ones for multiple labels, but you could have, as far as I know, previous work has only looked at one for each label because that's simpler. If the prompt itself is already virtual tokens, that actually doesn't prevent you from also applying this. So basically you would optimize the parameters of the prompt, you would optimize the parameters of the output, and you would be able to do all of them at the same time. It seems a little bit strange because suddenly like your input prompt and your output answer are all like moving away from natural language. But you know, you're still able to keep the parameters of the language model fixed. So if you only need to tune the parameters of the prompt and the parameters of the output token, that's actually not bad. That's not a lot of parameters. So it's still a pretty parameter efficient like tuning method. I have a question. What would be the ground truth in the case where we use a virtual token for the answer space? So the ground truth, like basically, I'm not sure if the people on Zoom can see this really well. But basically, you would have positive and negative, and then these would be mapped to the actual classes, like positive and negative. And the ground truth would be the ground truth label that you get from your data set, basically. So any of these like automatic search methods require that you have at least a little bit of training data in the task that you're interested in. Otherwise, you don't have any criteria with which you can do search. So, yeah. Yeah, so isn't this just like a fancier way of doing regular training for the model? Yes, basically it is, but I think one of the main points here is that I think this is a very good thing to think about. And one of the main points here is that if this is something that you can do reasonably well without doing any training. So if you can do it in a zero-shot scenario where you assign a prompt that is based only on like natural language and an answer that's based only on natural language, and you can still get reasonable accuracy, that means that before you do any training whatsoever, you're already in a pretty good place in the space, right? You're already doing quite well. And because of that, you have chosen a shape of your problem that is conducive to utilizing the pre-trained language model's parameters effectively. And because of that, if you can tune only a few parameters, or you can tune with only a few training examples and do even better than that. I guess like one way to think about it is if you can do well zero-shot, that greatly increases the prospects of you being able to do well even better in like a few shot scenario where you have very few training data, or even in a reasonably large data setting, because you're never going to have as much data as you have in your pre-trained language models, like pre-training data. So if you're able to use what you've already learned from the pre-trained language models training data effectively, then that will give you better prospects, I guess. Yeah, good, very good question though. It is a fancy way of doing training, but it's fancy in a good way, I guess. Cool. Okay, so another important thing is multi-prompt learning. So you can go from single prompts to multiple prompts. There's a couple ways you can do this. I'm only going to talk about the top two here, prompt ensembling and prompt augmentation, but the other ones are covered in the survey if you're interested. So prompt ensembling, basically what it's doing is it's saying, hey, there's actually multiple ways that you could ask the same question. And depending on how the model has been trained, or depending on specifically what examples it's seen in its training data, some of these might be more effective than others. So what you do is you want to express the is capital relation. So you can come up with like 3 prompt templates instead of 1, each of which is indicative, and then ensemble them together. So the advantages of this are that you can utilize the complementarity of the prompts. Also, because you don't need to find like any one single prompt that's like the best of all of them, you can alleviate the cost of engineering, especially when you're doing it manually. And you can also stabilize performance on downstream tasks somewhat. So some typical methods include just like averaging the probabilities from all of them, doing a weighted average where you learn weights for each prompt, depending on which one is the best. Also majority voting, which is kind of a variety of uniform averaging. So another thing is prompt augmentation. And this prompt augmentation, basically what it does is it's a way of adding a little bit of training data to demonstrate exactly what you want to be doing. So intuitively, the input is like add up two numbers, 6 and 8. And so what you do is you provide a couple other examples of addition beforehand, and then ask like this question. So actually, this, I realize now that this example is not super, like this input is not actually the input. The input would be like 6 and 8. So what you do is you add two or more other examples of addition before this, and then you do 6 plus 8 equals mask, and then hope the model is able to fill it in. And this is like actually a very effective way of kind of controlling your model. It's pretty amazing that models are actually able to like just read in the context and mimic the context. But it's something that all language models can do to some extent, because there's lots of other examples of that in their training data, but in particular, really large language models can do this pretty well. So if you do Q, Japan, A, Tokyo, Q, France, A, Paris, Q, Germany, A. Now let's see if this works. Might have to reload the demo. And the funny thing is, if it works, it will continue to generate a whole bunch of these for you. So. Pretty good, huh? So this is the idea of prompt augmentation. It's basically you give several examples of answered prompts, and then you add the prompt that you'd like actually like to answer.
There's a couple of mistakes that we
Yeah, and one thing to note is that language models are actually not that great a source of factual knowledge. They're like, where's the first one? Italy, Genoa, I see.
They wish.
Yeah. Right. So, but yeah, anyway, you can see how this works in general. Cool. So if you have multiple prompts, that's another thing that you can do. Cool. Any other questions here? If yeah. Yeah, and actually, I'm going to go directly into talking about that here. So we're going to talk about prompt-based training strategies. And there's two perspectives with which you would like to discuss this: data perspective and parameter perspective. Zero shot is without any explicit training data of the without any explicit training data for the downstream tasks. So this is basically where you assume you have absolutely no examples whatsoever, and you want the model to just perform well out of the box without any demonstrations. Few shot learning is where you have few training samples. There's no strict definition of few shot learning, but I guess my ideal definition of few shot learning is where you would have absolutely no chance of doing well on the task without a pre-trained language model. So, there's no way you could solve the task if you didn't have some sort of pre-training involved. If you have less than 100 examples, I think it's probably fair to call it a few shot. strategy. A full data learning strategy is where you have lots of training samples, like enough that you could do reasonably on the task, even if you weren't using any sort of pre-training. So, you know, like 10K or whatever else. So there's a lot of different prompt-based training strategies. We tried to come up with the typology of them in the survey that I'm basing this lecture on. The first one is promptless fine-tuning. So this is like what you typically do with BERT. And you know, you take it and you fine-tune it directly to solve your task. There's also tuning-free prompting. So this is like what is done in GPT-3 or, you know, in my examples from GPT-J, where we just provide a prompt. We don't change the parameters of the language model at all. There's also fixed LM prompt tuning. So this would be like prefix tuning. And prefix tuning, you know, we have individual parameters for each of the prompts. And we tune the parameters of the prompt, but we keep the parameters of the language model fixed. And then we have fixed prompt LM tuning. And this is basically where we use a standard textual prompt. So we have a prompt that is expressed in text, like, you know, Pittsburgh is located in this, but then we fine tune the language model to do well at this task. So the idea why you might want to do this, why this might be better than promptless fine tuning is precisely the answer that I gave to the previous question. Like, isn't this just a fancy way of training your model? Well, it is a fancy way of training your model, but because you start out with a prompt that already gives you pretty good performance, you would expect it to do better on fewer examples, generalize better, or something like that, because you're starting out from that good point in the space. And then if you want to go all the way, you could do prompt plus LM fine tuning. You tune all of them together. Maybe you start out with a prompt like this, but then you make it possible to fine tune the parameters or something like this. So there are also examples of this as well. So I have kind of a thing here, which is like, which one should you be using? If you have a huge pre-trained language model, you might just want to fix the language model and not change it. If you have few training examples, you could use one of the examples here, like tuning-free prompting or fixed LM prompt tuning. If you have lots of training samples, you might as well go for like tuning your language model. So I think that's a kind of general approach. And then I have questions here. I have two more papers that I'd like to introduce that I realized as I was talking that I didn't add to the slides, but they're very nice ones. So the first one is this one. So it's called True Few-Shot Learning with Language Models. And it kind of does a critical analysis of how well few-shot learning techniques work with language models. And basically, one of the interesting things that they talk about here is basically, we talked about methods to do kind of like search for prompts, like using paraphrasing or mining or stuff like this. And this gives us a big candidate list of prompts. And then we choose which one we use based on a development set. And what they show here is basically the size of that development set is actually super important. So if you have a small development set, you can't very robustly choose these. So then the question is this actually few-shot learning, right? You need a big development set to choose which prompts you should be using. So that's cheating, basically. So I think this is a really good paper, critical analysis of this here. And then another interesting paper that came out very recently, and I didn't have time to add to the slides, is this paper. And basically, what this paper does is it proposes a method called instruction tuning. And the idea is you basically do a very large multitask training of a language model. Specifically, I believe they're using a T5 model. I actually forgot that detail. Maybe, yeah, I'll have to check that later. But basically, what you do is you provide a prompt, and then you train the model to do well on the task based on the prompt that's provided. But you train it on a very large number of tasks. And because of this, now you have a model that basically has been trained to take in a prompt and solve a task. And so it's then you can do inference on unseen task types. So you can get a completely different task, but now you're given a prompt, you're given answer options, and it does better on other tasks. And this is quite effective, increasing kind of zero-shot accuracy or on new tasks by quite a bit more. And I think one particularly interesting result from here is that there's actually kind of an inflection point. I wish they had one more point in this graph. It would make the picture clearer, but still, it's a very interesting graph where, depending on the model size, you start out with this kind of instruction, the model that you train in this way by training it by seeing lots of prompts. And there's suddenly a point where you increase the parameters enough, you get a strong enough model that suddenly it becomes very good at working on held out tasks in addition to non-held out tasks. So this is a nice paper overall, but I think this graph is particularly interesting. So cool. Yeah, that's all I have for today. We're right at time. Are there any like final questions before we wrap up? Or? Okay, great. Thanks a lot, everyone, and happy to take questions up front.